This video we're going to look at similar triangles. In order to prove similarity of two triangles, we need to just prove that all angles are in the triangle are identical, or else the corresponding sides have been enlarged by the same scale factor, or you could say that the sides are in the same ratio. So we're going to look at a couple of examples now on our similar triangles, so proving things are similar and also finding missing sides in similar triangles. This first example says, prove these two triangles are similar. So I'm going to do this in a couple of ways. I'm going to look at the ratios of the sides. I'm also going to look at the angles. So I've got two triangles here. If you can imagine, I've got the smaller triangle here, and I've also got a bigger triangle here. So if I label these triangles, if I give them a name, the corners, the vertices of these triangles names, it will make life an awful lot easier. So I'm just going to call these sides here, I'm going to call this A, and then B and C on the big triangle, and then this on the small triangle, it's already got an A, and then I call it D and E. Now if we have a look at these and go through them together, then we'll just say that clearly the angle at A, they share the angle at A, so that really the angle, I'm going to use a three letters way of saying angle, so D, A, E, so that's on the small triangle, equals B, A, C on the big triangle. So I've shown that that angle is the same on both triangles. Next one I'm going to look at is this one here. This is a right angle, and also this angle here is a right angle. So I'm just going to say that A, D, E is a right angle, so that's on a small triangle. Likewise, on the big triangle, A, B, C is a right angle, so that's on the big triangle. So so far we've shown this angle they share, and these two angles are equal. We just need to look at this last angle and show that they are also equal. Okay, they are equal, and the reason they are equal, if you think about it, how you would calculate this angle here is you would do 180 minus this angle and also this angle, which happens to be 90. Same idea, how you would calculate this angle at C is you would take away this angle, which was the same as the one we had before, and 90, so they're bound to be the same. So we can just say then, also the angle AED is equal, so it was on the small triangle, is angle equal to angle ACB. So we'll just say all three angles the same, which implies they are similar triangles. Okay, that's one way of looking at it. The other way we're looking at it is we can look at the sides, sides being in the same ratio. So I'm going to draw out my triangle again. I'm going to draw my small triangle, which was 3, 5, and 4. And then my big triangle, then, which is, and that is 8. And 6 is the big side. And because that's a right angle triangle, you could work that out by Pythagoras Theorem, and that would be equal to the square root of 6 squared plus 8 squared, and if you work that out, it would work out to be 10. Sorry, that's not very clear. I'll write that again. That was the square root of 6 squared plus 8 squared, so it works out to be 10. And then we can see that from 3 to 6, you go from 3 to 6 by multiplying by 2. You go from 4 to its corresponding side of 8 by multiplying by 2. You go from 5 to its corresponding side of 10 by multiplying by 2. So we can say corresponding sides in the same ratio. So there's two ways of proving that the triangles are similar. So the last thing then, obviously that implies that they are similar triangles. Okay, that's that example done. So two ways of showing that something is similar, triangles are similar, showing all the angles are the same, so three angles are the same, or else the sides are in the corresponding sides are in the same ratio. Okay, we're just going to look at a few angle facts which are going to come into play, which are very, very important for our similar triangles. So we're going to look at these, and we've got 6 of them here. Supplementary angles. So this is a very, very easy one. This is just something that you've known from way down the school, and that's angles in a straight line are equal. So if I have an angle here, A, and an angle B, and together they make a straight line, then A plus B are said to be supplementary, which means they add up to 180 degrees. Okay, vertically opposite angles. So if you have an angle A and across away from it, you've got an angle B, then A is going to be equal to B. Angles at a point. So if I just do a point here, and I have a whole pile of angles coming into it, and then you would say that they would sum up to 360 degrees. And the reason for that, if you can imagine, I'm doing a full turn, that's going to be 360 degrees. Next one was alternate angles. So we need to draw our parallel lines here. So draw a wee parallel line, put a wee arrow on it to show it's parallel, and do your wee line which goes across it, and it's going across. It's called what's called a transversal. So A and B, they're on alternate sides of the transversal, so A is equal to B. And then the next one is our co-interior angles. So again, draw your parallel lines. And here, they are on the same side of the triangle. So A and B are on the same side. They're not equal, but A plus B are supplementary again. They add to be 180 degrees. And the last one is our corresponding angles. So corresponding angles, and I will do one here. So that's A. I will do one here. That's my A. If I can do a wee bit bigger that we can see it. And that's your B. Remember to mark on your arrow to show that they're parallel lines. And there we have it. So they are in the same place. So let's have a wee look at that. There's like 4 bits to this up on top here. And A is on the, so in this wee section here, A is in the bottom right. In this wee section here, B is in the bottom right. So that tells you then A must be equal to B. And that's it. Okay, these things are very, very important. So you've got your angles in straight line add up to 180 degrees. Vertically opposite angles are equal. Angles at a point add up to 360. Alternate angles are equal. Next one's in co-interior angles. So the C shape or the U shape add up to 180 degrees, and corresponding angles are equal. So they're very, very important that we understand all of these. This example is a very easy example. It says determine if these triangles are similar. So all we have to do is work out the missing angles in a triangle, and then if all 3 angles are the same in both triangles, then they're going to be equal. So this angle, very, very easy. To get it, you're just going to do 180 minus 55 minus 85. And if you do that, it works out to be 40 degrees. So just put that in. That's 40 degrees. Same idea over here. That's going to be 180 minus 55 minus 40. And it works out to be 85 degrees. So let's have a look at our triangles now. I've got an 85 degrees, I've got an 85 degrees, I've got a 55 degrees, I've got a 55 degrees, I've got a 40 degrees, I've got a 40 degrees. So I've got all 3 angles are the same. So they are similar. So all 3 angles the same, which implies they are, oops, if I could spell, similar. Okay, the next one is very similar to the sort of thing you would get in an examination, and it's to prove that triangles ABC and DEC are similar. Quite often this would be the first part of the question, and then it would go on to ask you maybe if you know they are similar, then find missing lengths. Hasn't asked you to do this in this question, you're just to prove they're similar. So I'm going to do this using a slightly different notation, but they're trying for us to prove here that ABC, so this big triangle, is similar to DEC. Now, we've sort of seen this in a previous example. We know they are going to be similar, but we're just going to go through this again just to prove that they are. So we will say, first of all, B, the angle at B, so this angle in here, equals the angle at E. And the reason for that is that they are corresponding. So they're corresponding angles. That's why they are equal. So if you can't see that, folks, just extend your line, and you'll see then you may have to rotate your page to see it, but you have got 2 parallel lines, and then you've got this is your transversal now going across, and then they are in the same corresponding in the same place. Okay, next one we have to do then, we'll do a very easy one. We'll do C. So we'll do C. The angle C is equal to angle C. So we'll just say they share that same angle. They share the angle C. That's dead easy. Then the last one for us to do is here. And my angle A and my angle D, again, might help us just to extend, just to see. There's my parallel line, so they are in the corresponding place. So my angle A equals my angle D, and again, that is because they are corresponding angles. So they are, just say, so three angles the same. So the triangles are similar. Done. Okay, this example says diagram shows two triangles, and you have to prove that they are similar first of all. So first thing, to prove that they're similar, for part A, I'll do my answer to part A up here. I'm going to show that my angle here, which is, and this angle would be ACB, and it's going to be equal to this angle, which is DCE. Okay, and that's just because they are vertically opposite. This angle here, which would be BAC, is going to be equal to DEC, and the reason for that is they are alternate angles. And my last one, so I'll put the wee double lines on that one. My last one, I'll put triple lines on it. My last one, I'm going to say that angle ABC is equal to this one down here, which is CDE. And again, it's because they are alternate angles. So we're only able to do this because they put these wee arrows on to show that the line on the top is equal to the line on the bottom. So that's how we're able to tell that those two things were equal by the alternate angles property. So it says prove that the triangles are similar. I've written down that the angles are equal. It hasn't really shown that they're, I haven't said that I understand that means they're similar. Just say, therefore, three angles are the same, so they are similar. Next part says, hence find the lengths of CE, CB, and DB. Now we wouldn't have been able to do this had we not known that these triangles were similar. So because they are similar, we can work through this. So I'll do B part 1 over here. Okay, so I'm going to go work out how I get from the big triangle to the small triangle. So my scale factor is going to be the small triangle, which is dimension, which is 10.4 divided by 16, which works out to be 0.65. Okay, it's unusual that I've done it that way. Now, the only reason, if I'm honest, that I did it that way was 0.65 is quite a nice decimal. Whereas if you do it the other way, it's a fraction. You would need to leave it as a fraction because it would be a recurring decimal. It would go on forever and ever. So it's just much nicer to leave it this way in this particular example. But if you do get a fraction, like say you got whatever it was, 13 over 20, leave it as 13 over 20, 13 over 20, or said it'd be 20 over 13, leave it as 20 over 13. It's ugly, but you can use that in your calculator using the fraction button on your calculator, this one here. So you would have, if you're going a little bit around, it would have been just 20 over 13 you would have used to get multiplied to get from small to big. But I just prefer to use the decimal in this case. So I'm looking at how you get from big to small. So to get from big to small, you multiply by 0.65. So in this case, CE was what we were looking for. So it was this side here. I'll just highlight it. This side here was the one we were looking for. So to get that side, you have to, it comes from the 11. So CE is going to be equal to 11 times 0.65. If you do 11 times 0.65, I got 7.15, and that's going to be centimeters. For part 2 of this question, we need to find CB. So CB, where is CB? CB is going to be here. So CB is this side here. And where does it come from? It comes from the 5.2. Now, CB is the bigger one, so it's going to be 5.2, and it's divided this time by 0.65. And if you do that, you get 8 centimeters. And our last thing we have to do in this question is we have to find the whole length from D to B. So that would be all the way from here to here. So it's just going to be those two lengths added together. So DB is just going to be 8, which we've just worked out, plus 5.2, which works out to be 13.2 centimeters, and that's it. Our last example says triangle PRS and PQT are similar. Calculate the lengths of PT and QR. And they have been helpful, and they've labelled PT with X and they've labelled QR with a Y. Now again, in this question, you've got a small shape here, which is enlarged to become this larger shape here. So the small triangle becomes a larger triangle. So you can, if you want, redraw this shape and work this and go from there. I'm going to do this using the scale factors. So I'm going to again say small to big, and we have one dimension which allows us to work this out, and that's this 5 centimeters on the small becomes 7.5 on the big. So 5 goes to 7.5. So that means my scale factor is equal to 7.5 divided by 5, and that works out really nicely as 1.5. Okay, so if we look here, to get the PT first of all, PT is here, it is X, and PT enlarges and it becomes X plus the 14. So we're going to say then that X goes to X plus, not 14, it was 1.4 if I could read, and it goes there by multiplying by 1.5. So you can say 1.5x is equal to X plus 1.4, and that means 1.5x minus X is equal to 1.4, which means 0.5x is equal to 1.4. I'll just finish this off here. That means X is equal to 1.4 divided by 0.5, which means X works out to be 2.4 centimeters. Okay, to do the next bit, then we're looking to find our Y, wherever our Y is. So Y is up top here, and Y is just this wee section. Wee bit trickier this one to maybe understand what's going on, but you've got 8 on the small, and it gets multiplied by 1.5, and it becomes this whole length here. So it becomes Y plus 8. So you could really say 8 times 1.5 is equal to Y plus 8. 8 times 1.5 would be 12 is equal to Y plus 8. Then 12 minus 8 is equal to Y. So Y is equal to 4 centimeters, and that is us done.